Hello and welcome to today's webinar entitled Polymers in Wire and Cable Applications, brought to you by the BPF and Plastics Consultancy Network. For today's webinar, your host is Dr. Trevor J. Hutley, a polymer consultant with international technical and management experience within the plastics industry. His varied skill set ranges from research and innovation, product development, technical services and application and market development. Trevor is a specialist in polymer materials, additives, formulations, and structure property relationships. He's also been a member of the PCN for more than 20 years. This Lunch and Learn webinar focuses on the wire and cabling sector. It highlights the subdivisions within the industry, its drivers, the polymer materials required and terminology used in the industry. By the end of this webinar, you should be able to understand the key polymer materials used for the insulation and how these polymers are typically formulated and modified to achieve certain properties and performance for wire and cable construction. Before I hand over to Trevor, just a quick reminder that you can pose your questions to us by submitting them into the questions box on the GoToWebinar control panel. And with that, I'm going to hand over to Dr. Trevor.
Thank you, Miami, and good afternoon to all those who've connected to this Lunch and Learn webinar. As Miami introduced me already, I am a polymer consultant. I'm British. I've worked overseas many years of my life in the polymer and plastics industry, and I've become a specialist in polymer materials, formulation, structure property relationships. And I've been an independent consultant for more than 20 years and a member of the Plastics Consultancy Network for that amount of time. So the overview of what we're going to cover today in about 40 minutes is just to talk, as I did in my previous webinar, a little bit about the product lifecycle webinar series that we, the Plastics Consultancy Network, have put on. This is one part of it. Then look at the markets and applications for plastics, the growth of the plastics industry, and then focus in on the topic of today, which is for polymers in electrical and electronic and wire and cable applications. Look at some of the drivers and trends for polymers and their application in these sectors, and some of the properties and the actual applications, some images and some pictures and some discussion on those topics. So I've called this an overview. It's not a content in the sense of what is exactly in the book, but it's more a journey through this area, and we'll go into and out of various aspects of this. But this is the overview of what we're going to cover today. So the BPF, as you may be aware, have a very extensive Lunch and Learn webinar series, of which this product life cycle series put on by the Plastics Consultancy Network is just a part. So we are the Plastics Consultancy Network, and we have been serving the polymer industry since the late 80s. And we're a professional network. We're not a company. We're just a network of some of the most experienced independent polymer consultants in the world. And we came together in response to our dialogue with the BPF to put together this series of webinars, which we've called the product life cycle. So this series provides a brief introduction, because we only have 40 minutes every few weeks, a brief introduction to many of the topics that are critical to understanding the development of plastic products. It's not life cycle in these terms as we're used to in marketing, where we talk about introduction of a product and its growth and maturity and decline, but it's more about the life from a polymer material to a plastic product. And I thought one way to look at this perhaps more helpfully is to think about the polymer industry value chain. And those who were in my previous webinar will see that this introductory part is very similar to what we've talked about before. But the polymer industry value chain is that series of activities which increase the value from the feedstock, which we're not going to talk about today, but through the polymerization of the monomers, the formulation and compounding of materials, the processing of those polymers into the application. And we need to always bear in mind that the performance of a plastic product is a function of the material and the design of the part and the processing by which it has been made. And then we get finally to the OEM, and maybe this is a bit of an automotive terminology, the original equipment manufacturer. For example, today would be a company like ABB, one of the big power cable manufacturing companies. And then the customer, that is the person who pays, which may be the national grid of a country, or it may be us as the consumer who pays our electricity bill every month. And then we have to look at the end of life, and that's not the topic of today. That's going to be covered by other colleagues in later webinars. So if we go along the bottom of the value chain here, monomer, polymer, these perhaps more familiar terms that we're used to. Monomer, polymer, plastic material. We think about design, rheology, flow, processing, the properties, and then now we think about the circular economy. So that's the polymer industry value chain. And this product life cycle series looks at these phases of the life cycle of a product. It looks at materials. We've done that already. We've looked at the design. We've looked at manufacturing. And this is where we are now. We're in the area of the applications of plastics materials. And then we're going to be looking in later webinars at the end of life and also about managing the product life cycle, particularly looking at how to recruit, retain and motivate the right people to perform all of the above tasks. So this is where we are, applications at the moment. This is the topic of today, applications of plastics materials. And coming up in the next few weeks, we have a webinar by Sarah Greenwood on packaging and sustainability, 11th of May, followed by 13th of May, Keith Freegard talking about a resource efficient economy. And then finally, I believe in this section, end of life, Terry Cooper talking about the end of life challenge for flexible plastics packaging. So now we're coming to today's topic, which is polymers in electrical and electronics sector, E&E, and wire and cable applications. So wire and cable is part of the electrical and electronics market for polymers, and wire and cable is a global growth industry. It's growing at a compounded annual growth rate of more than 8% per annum. And it's been estimated that in 5 years, it will use about $22 billion worth of polymers. And in this webinar, we try to introduce this market and this sector, wire and cable sector, and look at some of the electrical and other properties of polymers which are important for this sector. And I think it goes without saying that electrical, electronic and wire and cable applications, they are everywhere around us, whether it's AirPods or whether it's the phones that we use, the iPad, every device and everything that we touch and use somehow includes electrical and electronic applications of materials and cables which provide the electricity, the power, the data, the information that we need in our everyday life. So polymers are used extensively in this area. Now, looking at the big picture, which helps us understand a little bit more about this sector. Look at the big picture, as we saw in the previous webinar. If you look at the world plastics production, and we kind of start from 1950 because that was the first year when the production was above 1 million tons. Without going into any detail of this, this is my evergreen chart continuously being expanded year by year about how many millions of tons of plastics are produced each year in the world. And now in 2021, we're at about 361 million tons. Think about it like this, 1 million tons of plastics produced every day. This is a very large quantity of material, and if you just look at the shape of the graph without looking at any details or any numbers, you can see this is an industry that's on a growth curve. This is a fast growing industry, and it has been for the past 70 years. So what is it that drives this plastics industry? There are a number of factors, a number of drivers. Demographics, the increasing population, all consuming more plastics materials. Progress of society, as we become more sophisticated, we require more materials and more packaging, more functionality. We've seen a geographical shift in the last 20 years to the Asia Pacific region, which is now kind of the center and the hub of everything to do with materials. And this is a big feature, and we'll perhaps come back to this a little bit today from time to time: material substitution and technological progress. As technology becomes more sophisticated, we require better and more functional materials, and materials that were previously used are being substituted. At the time, they were the right materials, they were the best materials. But as the progress of technology goes on, those materials get substituted. And that's the reason behind a lot of the growth of the plastics industry. And new market and application opportunities are opened up by new plastics materials with new properties and new capabilities. And then finally, there's the feedstock story. Whether we are building a plastics industry based on carbohydrates or hydrocarbon, so-called fossil fuel feedstocks. We won't get into any of that controversy today. But interestingly, the polyethylene industry, which started with the accidental discovery in 1933 of polyethylene, was made from ethylene that was made from ethane that was made from ethanol by fermentation of sugar beet in the UK. So very first polyethylene was made from a biological and renewable source. Interesting when you look back on the history. All right, so material substitution, keep that in mind and see if that's a theme that we detect as we go through today's story. As we looked at before, the market for plastics, markets of plastics can be found to be quite similar around the world. Almost always the largest market is in packaging, followed by building and construction, and then automotive, as we looked at in the previous webinar. And usually the fourth largest market for plastics and materials is electrical and electronic. And you see that I've positioned the circle here to overlap a little bit with automotive, because we specifically didn't cover this last time. And we've also overlapped with building and construction, because as you're clearly aware, that no building, no construction can really take place these days without an enormous quantity of wire and cable for supplying power and data and information throughout. And then there are the other market sectors which we're not looking at today. And we took some numbers for the European applications, and so the packaging was almost 40%, building and construction 20%, and automotive just under 9.6%. That's the latest European numbers. And for electrical and electronic sector, 6.2%. And actually, if you look around the world, you find that electrical and electronic is usually the fourth largest application sector, and it's somewhere between 3 and 8%, depending exactly where you are. So that's the story. We're looking at the fourth largest market for plastics, and bear in mind that these largest market numbers are based only on the tons of plastics, not based on the value, not based on the value in use, only on the tonnage. So let's get right down to the detail of the electrical and electronic market sector, fourth largest market for plastics. And wire and cable is part of that. Wire and cable materials, as I said before, is going to be soon more than $20 billion. The wire and cable business itself is soon going to be $293 billion business. Very, very large business. And what specifically can we find within this sector? Let's just take a highlight of this. Automotive, which we've looked at before as an application for plastics, but we specifically didn't look into these areas. We didn't look at the automotive applications for plastics in the electrical and electronic and wire and cable sectors. We're going to look at those briefly today. Electrical and electronic market, I've just taken a number of ideas here of where plastics are used. The full details of plastics used in electrical and electronic markets, you'll see in the reference right at the very end of this presentation. It's actually a table that goes on for 5 pages, 150 different applications for polymers and electrical and electronic. Very, very diverse and broad. And then the other subsector, wire and cable, we see wires and cables of every kind everywhere for communication, for data, a coaxial cable for signals, networks, power transmission, power distribution to our homes, to our factories, fiber optic cables, photovoltaic systems. And each of these could itself be looked at in great detail, but we're just going to look very broadly at this. So there's in one slide there's a kind of an overview of the 4th largest market for plastics. We're going to look quickly at some of these today. And as we did before, I want to consider, before we start in the detail, looking at the features of plastics that are particularly important for this sector. And perhaps not surprisingly, I've chosen as a priority here the insulating properties of plastics materials. They can be easily shaped, very easily processed. Part and function consolidation has always been a source of value creation in plastics applications. So integration, part and function, freedom of design, ease of assembly, and a great feature that we will cover a little bit today is how the properties of plastic materials can be tailored by very careful formulation to get the exact balance of properties that you require for your application. Relatively low cost materials, they are self-colored, as the image here shows. You can have insulation, not just black, you can have insulation of wires, any color that you choose. They're durable. Fortunately, when we put wires and cables into buildings or in submarine cables, they're going to be there for 20 years or 30 years or 40 years. They're durable. They can be transparent, which is useful in some in cases, for example, in fiber optic cables. Relatively low density compared to metals, particularly when you're preparing very large cables, as we're going to look at today, power cables, low density materials. That's generally a feature of plastics materials versus metal. You could say the typical density of plastics materials is 1 to 1.5. I know some go above 2, but relatively low. So let's look at applications of plastics materials in automotive, electrical and electronic applications and wire and cable. And it's interesting that if you take Audi's latest images for moving towards a lightweight electric vehicle, every feature of this is focused around the lightweight, and actually only at the very location here, when we talk about the high voltage battery as an integrated component, do we mention anything to do with electrical and electronics. But this is the focus here for the Audi, is to get the weight out of the vehicle. Now, if we look at another vehicle and look at it from the point of view of electrical and electronic systems and sensors, then we suddenly realize that the car is completely full of devices, systems, sensors and mechanisms for now and for the future that employ plastics and polymer materials in a variety of applications. I'll leave you to study this in more detail. These, by the way, these slides will be available on the BPF website afterwards. And sometimes, for the sake of time, I've put something in the slide, but I don't even discuss it during the presentation. I just pass over it. You can look at the details in your own time. So in automotive applications, some of these are very, very old and some are becoming a bit newer. But lead acid battery cases, there will be a time when people say, hey, what is that? What are you talking about? Lead acid battery? These cases now, polypropylene materials, smart designs, wire and cables in cars is so many connections and cables and housings and fuse holders and connector systems and plugs, connectors, and even the humble spade terminals still rely on plastics materials for the insulation properties. So these are kind of a bit in the past, they're current or in the past, and perhaps now we start to look a bit more towards the future. Now we start to look at how for example, in the Tesla, how everything is now integrated into one 15-inch display. Perhaps that's going to be the future. You don't any longer need the complexity of dials and knobs and switches. Everything is done by voice, by a gesture, and through the screen. And the batteries that we look at now are very, very different in terms of their size. And we used to think of a lead acid batteries being heavy, 5 kilos, 10 kilos. Now we're talking of 500 kilos. And of course, motors in cars are not new. They've been used to actuate seats, to actuate mirrors, and in the old days, even to actuate aerials, radio aerials in cars. But now the motors become the drive for the vehicle. But there's still a lot of innovation going on in this area. We hear a lot more about the batteries, but there's a lot happening in the motors themselves. Mostly material related. For example, Tesla now using permanent magnets to reduce the electrical demand on the electromagnets. And I saw that Honda has started to use square copper wire to get more wire packed into a smaller space. Sometimes these are lateral thinking solutions. The audio systems in cars use plastics materials, polymer and mica composites, to achieve different levels of performance and lower weight. It's still one of the challenges in the car, is to get this level of audio performance and reduce the weight. So there we are, a quick overview of perhaps where we're going in some of the future areas of plastics applications in automotive. So what are the drivers and trends for polymers in electrical and electronic applications and wire and cable? Actually, we looked in the webinar before in automotive about some of the dynamics of the automotive space. And in this case, where we looked at the so-called access drivers, 4 out of 6 of these are clearly having an impact on electrical and electronic and wire and cable applications for polymers. And then we looked at an alternative set of drivers for the automotive space, and in this case 8 out of 9 of these drivers also require electrical and electronic applications of polymers and more wire and cable applications. So a lot of what's happening and going to happen in the automotive space is going to be a driver for polymers in this sector. And electronics industry growth itself is going to be a driver. The trends towards miniaturization, multifunction are all possible because of the use of polymer and plastics materials. Another factor is this continuing trend to rapid urbanization of the world, which requires more infrastructure, more buildings, more construction, and more connectivity. Another growth driver is the increased demand for electricity. As the portfolio of energy supplied to the world changes, there is an increased demand for electricity and an increased fraction of the energy spectrum that's going to be supplied by electricity. These are all drivers for more polymers in electrical and electronic applications. And I thought this was an interesting kind of global perspective on this, that last year, whilst the world was, and still is, but last year particularly, while the world was suffering from the impact of the COVID-19 pandemic, that the approach of the People's Republic of China was a little bit different. Instead of supporting industries to kind of get through the pandemic, they accelerated their investment in 7 new priority areas in 5G communications, artificial intelligence, the industrial Internet of Things, data centers, electric vehicle charging stations, intercity high-speed rail, and ultra high voltage electricity transmission grids. Now, these are not just ideas. We're talking of multi-billion-dollar investment just in the transmission grids. I saw they invested $26 billion, I think, in this already in the last year. And of course, all of these areas of investment, I think all of them without exception, are all drivers for polymers in electrical and electronic applications and more wire and cable applications. So there are a number of drivers for the growth of this sector, but perhaps we'll take this last one here, the electricity transmission grids, as being the basis for some of our thinking right now. Now, if you look at the generation of electricity, and this is a picture from China, the issue here is that the generation is in places where there's wind and where there's space, but it's far, far from consumption. So that's why the grid development over very long distances, many hundreds and thousands of kilometers, is underway to move the electricity from where it's generated to where it's consumed. And as we look at high voltage direct current power transmission cables, one of the key factors in their success and development and growth is the development of the insulation material, the cross-linked polyethylene, XLPE, cross-linked polyethylene insulation for these cable applications. So you can go now to much higher voltages than was previously possible. And this means that you can reduce the cable weight of transmission capacity, reducing the investment required as well as the operating expense. And the kind of insulation material that ABB is one of the big power transmission cable producers is using. The cable insulation material was developed with Borealis, one of the big players in the wire and cable industry. And as we go to more and more requirement for very high resistance for insulation, you need to have very pure and very clean materials. So it's about production as well as formulation. So let's have a look at some of these cables which are made in very large scale for high voltage, very high voltage power transmission, very large cables. The previous image was being built in the factory and now being packaged and stored on a ship ready to be laid directly into the sea as a submarine cable. And the very latest one, running at 525,000 volts, is a cable that weighs, I think, 9,000 tons in total. So it's an enormous exercise in cable laying. But some of these as well, and some parts of the same project, are actually underground rather than undersea. And these are very large cables on very large drums and reels here. Very large. And they can weigh, of this order, 60 to 80 kilograms per meter. Very large, very heavy. But let's have a look a bit more in the detail. What do they look like inside some of these underground cables? So we break it down. First of all, of course, we have the cable conductor, aluminium or copper, then the cross-linked polyethylene insulation. We often have here a water barrier combined with swelling tapes, which we'll come to in just a moment. And then finally, a sheath of black polyethylene to protect the underground cable. Now, the cross-linked polyethylene insulation, it's a recent invention. It sounds like the quality of cross-linked polyethylene that's required, the purity that's required, is a recent invention. But cross-linked polyethylene actually was developed back in 1963, so actually 60 years ago, almost 60 years ago. So it's got some history. Cross-linked polyethylene. It's a way of improving the thermal performance of polyethylene in cables. So let's have a little bit more detail of the so-called swelling tapes that they describe them as. Normally, I would call these water blocking tapes based on super absorbent polymers. It just happens to be a topic, super absorbent polymers, that I've worked on myself for a number of years. And the super absorbent polymer is a very hydrophilic, that is water-loving synthetic polymer made primarily from acrylic acid. And these polymers are able to absorb up to 1,000 times their weight in water. That's an incredible statement just to think about it. 1,000 times their weight in water. And they form a hydrogel. So water goes from being a liquid to becoming encapsulated in the gel. So that's what they are. These materials, they can be made into a thin tape and incorporated into the cable design in order to absorb any water permeating the cable or entering through slight damage. So super absorbent polymers, tapes in underground cables. We don't have the time in this webinar to go in the detail of the polymers that are used in wire and cable compounds, but in general, I would say these materials tend to be elastomeric, and they have to be formulated to have high levels of solid flame retardant materials and also maintain the other desirable properties of plastics: ductility, flexibility, and toughness. And that is the formulation challenge for this particular sector. This is the whole list, so you have to look at that and study that in detail in perhaps in your own time. But we take materials such as ethylene vinyl acetate, or in this case ethylene ethyl acrylate, materials which have polarity and therefore can bond with mineral fillers and flame retardants and additives and contribute towards the integrity of the challenging formulations that we have to work on. So some of these materials are used only in very small quantities and in very specialized applications. Like, for example, PEEK, one of the earliest applications I remember for PEEK, polyether ether ketone, very expensive polymer, was as a cable wire covering in aerospace, where the properties and the lightweight can justify the price of polyether ketone. But for many other cases, more normal commodity polymers are used. If we look at polymers in electrical and electronic applications, typically molded parts, we can use both commodity polymers and engineering polymers. And I've kind of included here the slide from before and from my other presentations on teaching about polymers. Engineering polymers are those which perform typically above 100 degrees Celsius. Commodity polymers fall just below that level. Again, study that Amoko pyramid in more detail later. But the kinds of materials that we've worked with in this area, thermoplastic polyesters, PET and PBT, liquid crystal polymers, nylons, nylon 6 and 6,6, and the commodity polymers such as polypropylene, high density polyethylene and ABS. These are found throughout the electrical and electronic applications. And we take something, perhaps you don't see it because it's hidden away in the control room or somewhere in the basement of your house, circuit breakers, nylon-based materials which have the properties required for that kind of application. I took one example from my own past. It's a bit dated, but it's interesting because it's an application of an engineering polymer, DuPont rhinite. When I worked for DuPont Engineering Polymers Research, PET can be used, most people think of it as a bottle material in packaging, but it can be used as an engineering polymer. And we used this at the time for a customer, BJB, which was and probably still is one of the biggest lighting suppliers maybe in the world. At the time, they were making 600 million lamp sockets a year. And of course, nowadays people say, well, what's a lamp socket? They're still in use somewhere. But this was a conventional lamp socket at the time. This is just an example of a PET lamp socket. It didn't look like this, but we had two challenges at the time to meet to get PET engineering polymer into these applications. We had to reduce the outgassing and we had to reduce the discoloration, and that was a challenge that took a number of years basically to work on, to simplify the formulation, because rhinite can be a very complex material in terms of formulation, maybe up to 17 ingredients, and we needed to move towards simplification, and we needed to understand in detail the application requirements. Batteries, we use them everywhere and we don't see them very often maybe, but the lithium polymer battery or lithium ion polymer battery, rechargeable batteries, they're the basis of all of our mobile devices. Even the device that I'm using right now to speak to you contains a large lithium ion battery. And we forget, we've moved from lead acid batteries to lithium polymer, 1/10 of the weight, 1/3 of the volume, 10 times the power density, conformable shape, they're dry, there's no fumes. So now they look like this. I recently replaced a battery in one of my other laptops. You see the connector at the top there, and in the phone also. So batteries are a big part of our life these days. Use polymer-based materials and connectors throughout. I want to quickly look at some properties of materials that are important for us. The electric field, conductivity, flammability, electrostatic discharge, electromagnetic interference. And the applied electric field, when you take a material and you put a charge, a field across it, there are three things that can happen. First, the charge in the material can flow, and then you have a conductor. as in this case a copper wire. You can have no flow of the charge in the material, in which case we define it as an insulator. And the third category is you can have a reversible displacement of the charge in the material. It becomes polarized, and we call that a dielectric. So a dielectric is a material with insulating properties, but which polarizes under the effect of an electric field. We'll have to move quickly through these, but electrical conductivity is a key. I made a kind of an image here of the spectrum of electrical conductivity from conductor on the left there right through to insulator on the right, and we can put metals on there, we can put conjugated polymers that have been doped on there, and conventional polymers over on the right. As we all know, conventional polymers are insulating materials, and they have various levels of insulating properties, which are listed there in the order of insulating capability. And of course, PTFE is right out there on the right-hand side. Electrostatic discharge is another way of looking at polymer electrical properties, but here we're concerned more about the surface rather than the bulk conductivity and resistivity. Conductive materials, static dissipative, anti-static, and insulating materials. And there are various applications, particularly in the electronics industry, where we require the removal of static electricity, because even relatively low voltages like 20 volts can damage electronic components. I wanted to look at flammability because it is an issue for plastics and polymer materials in wire and cable applications, and we should be familiar with these three elements of fire. You need the fuel, the oxygen, and the heat. And the mechanism by which these flames burn and what we find in them are the free radicals. And we found at one time that halogens were great for quenching these free radicals and putting the fires out, but they've really been kind of become unfavorable. And so what have we had to do now? We've had to develop a different approach. We've had to find materials that could generate water, steam, carbon dioxide, and also coatings that could form on the polymer, intumescent coatings, to be a barrier to the fuel being in the fire. And that's how we've ended up with the category of materials known as low smoke, zero halogen materials in the wire and cable industry. And this has become an area well established now, that either magnesium hydroxide is used as a inorganic filler, produces steam at 330. Alumina trihydrate predated that and produces steam and water at 230 Celsius. And there are also naturally occurring mixtures of hydromagnesite and huntite, which are kind of mixed magnesium calcium carbonates, which produce carbon dioxide and absorb heat in the process. And the intumescent coatings, they come from phosphoric acid and from zinc borate, which can both form intumescent layers. And this whole area of flammability and fires is really being studied in some detail over decades, looking at the energy and the combustion energy of plastics materials. There's a continual pursuit, better understanding of fire, flammability, the effects of it, the impact of it on society, and what are the options for developing new flame retardant materials. Electromagnetic interference and emissions, we'll pass over that quickly for the sake of time here, but how to address it from the point of view of polymer materials. We have to shield components by the use of conductive materials, and we can look at the shielding effectiveness. And we can do that by surface treatment of housings with metal layers, by metallization, conductive paints, using materials with conductive components, amorphous aluminium flakes, stainless steel fibers, nickel coated graphite, and we can formulate them and add them to plastics materials to make them more conductive and more effective at shielding the electromagnetic interference. Now, remembering that 20 decibels of shielding is effectively 10 times better at shielding. So we're talking of 10, 100, even maybe 1,000 times better shielding by the use of various percentages of additives. And we have to be very careful as well how we compound these additives. If we put too much shear into the formulation, we can break down the agglomerates, which give us low shielding. We can actually break up the fibers, which also reduces the shielding, and we're looking for that optimum dispersion in the middle to give us the optimum shielding. So compounding is not only about formulation, it's not about just selecting the additives, but it's about the compounding technology as well. Let me move quickly on here to look perhaps finally at how wires are made. Again, it's a polymer process that starts with thermoplastic extrusion. We use a crosshead die and we pass a metallic conductor, the copper wire, through the crosshead die, and the plastic melt material is forced by pressure generated in the extruder through the crosshead die, and it becomes a coating onto the wire. And that's basically the technology. It's well-established technology. It's been used for many decades to produce insulated, coated aluminium and copper wires. So a little bit about how the wires were made. And that kind of brings me to the end of this very short webinar. We've looked at the product life cycle. We've looked at markets and applications for plastics, with a particular focus today on some electrical and electronic applications and wire and cable applications, particularly in power transmission. And we looked at the whole range of drivers and trends which are going to keep this industry, a growth industry, growing probably 8% a year for the next 5 to 10 years. And we've understood a little bit about the properties of these polymers, their electrical properties, their flammability behavior, and how that impacts their applications in wire and cable. And some acknowledgements and references just to finish here. I've used a lot of ideas, data, infographics from a variety of sources, which I've used freely in this presentation for educational purposes. There's no commercial value in this webinar. There's a couple of references for you. Special Chem, of course, always have a lot of detail about every one of these techniques. The book on polymers for electricity and electronics by Dr. Drobny is very helpful. And Michel Biron's book on materials selection for thermoplastic parts. He has a table there in his book of 150 examples of thermoplastic applications in electrical and electronic applications. If you're interested, I could always send you those pages. So that's the end of this webinar. I hope you found it a useful ramble and journey through this topic, and now the floor, as it were, is open for questions. Over to you, Miami.
Great stuff. A very good and insightful presentation there. Thank you so much, Trevor. I have one question. So you mentioned that flammability is being studied further in relevance to obviously wires and cables. With that in mind, what's the process for testing wires or cables for compliance?
Well, this, I believe, itself is a subject of an entire webinar, but I think the study of the flammability of wire and cable materials starts from the very basic testing, which has become more sophisticated, using cone calorimeters to study the energy that is produced by the burning of plastic material. So, for example, that graph that I showed you by the picture of an aeroplane burning, that's one of those graphs produced maybe 20 years ago, where people started to look in detail at how the energy has been consumed and produced by plastic materials. And then we measure the toxicity of the gases that come off. We measure the density of the smoke that comes off, and then the hazardous nature of some of those materials. And we try to estimate the time for people to be able to clear a building. And then there's the actual testing of wire and cables themselves, which is a very large scale activity where you need 2 to 3 meters of cable exposed to fires. There are many videos available on YouTube, as always, which show how this testing takes place. So there's a whole activity from theoretical right through to the hands-on practical testing of meeting the UL 44 requirements. There's a whole range of regulations and definitions, and even the definition of what you call low smoke and zero halogen, very tightly controlled, and people use it very loosely in marketing information. So you always need to tighten up and ask people that kind of detail. Is this really zero halogen? I've seen cases where cables use a zero halogen sheath, but inside there are halogen-based materials. So you have to be very careful what you write. You have to be very careful what you read. And as always, you need to go into these topics in one level more of detail to be aware of it. Hope that's given some kind of an answer to that question.
I'm sure it has. And then I've got another one, which might be something of relevance to people listening. What's the difference between thermoplastic and thermoset insulation?
Well, thermoplastic materials is kind of one of the primary classifications of polymer and plastics materials. Thermoplastic materials are those which can be melted and processed and then solidified, and then they can be remelted and reprocessed and resolidified. Whereas a thermoset material is a material that can be processed by heat and pressure, but then a chemical reaction takes place which makes it stay in that shape or in that structure for the rest of its application life. And the cross-linked polyethylene is an interesting kind of hybrid material because it's an insulating material that is applied. It's a thermoplastic material that's applied by an extrusion process to a wire or to a cable, and then the formulation of it includes additives which later, either in the presence of the heat of the extrusion or in the presence of moisture, cause it to cross-link and therefore become a thermoset material. So cross-linked polyethylene materials, as used in wire and cable, cannot be thermoplastically reprocessed because they become a thermoset material. So actually, I had a project on this many decades ago when I worked in Dunlop Central Research. We called it post-fabrication cross-linking. You use the advantage of thermoplastics for fast processing and ease of processing and ease of shaping and the economy of that, and then you combine that by post-fabrication cross-linking using electron beam or by using peroxide or by moisture curing technologies, gamma radiation, to cause the material to become thermoset and have higher thermal performance than would normally be the case. So that's how we think about thermoplastic and thermoset materials.
Excellent. Cool. And obviously you touched on one of the big drivers being automotive. Obviously you did a webinar about that previously, so I want to urge anyone who's listening and wants to hear more about the automotive sector, do give that a watch and have a look at our other webinars on there as well. Yeah, so I think that's all we've got time for, I'm afraid. Thanks again, Dr. Trevor Hutley, for today's webinar. Before I do sign off, just a quick mention of a few webinars we have coming up in the next week or so. So tomorrow we have the Understanding the Ongoing Global Shipping Crisis by SP Global. And then I'm just going to get the other ones up now. Next week we have the navigating recycled polymer supply in 2021. So give that a listen as well if that's of interest. And as Trevor mentioned in his presentation, we do have more of the product lifecycle series webinars coming up, the first of which is coming up on the 6th of May at the earliest. So yeah, that's all. Do you have any more final words, Trevor?
Well, I just hope that in these last two webinars in automotive and wire and cable, that people have had their imagination for the future growth of the plastics industry activated. We hear so much in the press that seems to be so negative about plastics materials, but they're great materials. It's a great growth story, and it's going to be definitely a big part of our future and enable us to meet all of our future desires and trends for mobility and communication and infrastructure and power. So I remain, after many years in the industry, very positive about plastics, materials and applications, and always happy to dialogue with people listening on that topic.
Very well said. And your details are on the presentation slides and the video when it goes onto the BPF website's archive page there. We have had a compliment, and it reads very informative, Trevor. So thank you so much for your time, and to all those who have listened in. So yeah, I will speak to you guys soon, and Trevor, we hope to work with you again very soon.
Okay, thank you, Miami, for taking care of it today. Bye for now.
No worries. Cheers. Bye bye.